Hi, I'm Norman Wappeler. Today we're going to introduce many of the most important formulas of classical spherical trigonometry. These are formulas that have been around for sometimes thousands of years, and they've been extensively studied, and many variants of them have been produced as well. This lecture is going to be an overview of the main formulas. We are not going to prove the main formulas. In fact, I think many of the formulas are logically a little bit dubious. What we are going to do ultimately is transcend all these formulas. We're going to present a new and far superior framework for spherical trigonometry, where all these formulas are replaced with different formulas with dramatically simpler formulas. But I would rather start by showing you the classical setup. So classical spherical trigonometry involves distances and angles on a sphere. Let's start with the idea of spherical distance. Here's a sphere. Here are 2 points, A and B on the sphere. Here's the line through A and B, which is a great circle. That means it's the meet of the sphere with a plane passing through also the center O. Now these 2 points, which are on the surface of the sphere, subtend an angle at the center of the sphere. In other words, if you're at the center of the sphere and looking up at A and B, you've got 2 lines coming out, there's an angle between those 2 lines. And the spherical distance between A and B is defined to be this angle times the radius of the sphere. So it's a proportionality between the angle and the distance. Now, many formulas of spherical trigonometry become easier to state when we look at the special case when the radius is 1. In that case, the distance is exactly the angle. So spherical distance and angle subtended at the center become exactly the same thing. The other notion we're going to need is the angle between 2 lines. So if we have 2 lines on a sphere meeting at a point A, then those 2 lines determine an angle. And there are at least 3 ways of thinking about the definition of this angle. Here I'm calling it alpha. The first definition is to think just in terms of a surface of the sphere near A. So we're looking at a local planar approximation to the sphere at A. If we're very close to A, then the sphere is almost flat there, and the 2 lines going through A are almost straight lines. So if this is the linear approximation to the sphere at A, we have our 2 lines now actually looking like straight lines approximately. Then we can just look at the Euclidean angle between those lines. Now admittedly there is more than one angle floating around here. We could take this angle, or we could take this angle, or possibly we could even take something like this. But we'll generally take the smaller of the angles, generally speaking. Okay, now there's another way of approaching this angle, and that's to think in terms of the 2 planes which are determined by the great circles. So this line is a great circle. It determines a plane through the origin. This line is a great circle. It determines another plane through the origin. So those 2 planes meet along a line. Here's the picture. So one of the planes, this one here, the other plane, this one here, and they're meeting. And they meet along a line. Something like this. Okay. So if you have 2 planes which are meeting along a line, what do we mean by the angle between them? Well, it's the angle, right? But what exactly does that mean? Well, you can think of it in this way. If you choose a vector which is perpendicular to this line, lying in one plane, and you choose another vector lying in the other plane, which is also perpendicular to the common line, then you have two vectors. So for example, if we have two planes meeting along that line there, one vector we could choose would be a vector in that direction there, which is perpendicular to the common line in the direction of the plane. And on this plane, there's the common line, we could take a vector lying like this. So we would have two vectors, one in this direction, one in this direction, and those two vectors make an angle. And that's the angle alpha. There's a third way of thinking about it, which is in terms of the normals to these planes. So if we have a plane in space, then it makes sense to talk about a normal to the plane. That's a vector which is perpendicular to the plane. So what we can do is we can choose for each of the two planes, we can choose a normal vector for each one of them. They each have a normal vector, and if we put those normal vectors together so that they're touching, then we can measure the angle between those two normal vectors. And again, there's a little bit of a choice. It depends on which direction you take, which vector of the two possible normals you take in either of the two positions. Maybe that's made clear by this cross-sectional picture here. So the two planes are represented by these two black lines. We're looking at them cross on, so cross-section. And the normal to this plane is this line here. And the normal to this plane is this line here. And then the closer those planes are being together, the closer the normals are to being together. And the angle between the planes is the same as the angle between the normals. So three different ways of thinking about the angle between two lines on the sphere. In other words, the angle between two great circles. Now let's talk about our notation for a spherical triangle. So we suppose that we have 3 points A, B, and C lying on a sphere. Here they are right here, A, B, and C. They determine 3 lines and 3 spherical distances. Distance between A and B, distance between B and C, and the distance between C and A. And we're going to call those, or label them, little a, little b, little c, in such a way that the spherical distance little a is the one opposite the vertex capital A. So little a is the spherical distance between the points B and C. And I remind you that means that's the angle subtended by B and C from the center of the sphere. So we're calling it a distance, but it's actually an angle, because we're going to assume that the radius of the sphere is 1 for simplicity. Similarly, the spherical distance B is opposite the vertex B, and the spherical distance C is opposite the vertex capital C. Now we also have the 3 angles formed by these lines. So we have the angle between this line and this line, that angle there. And what are we going to call that? Well, the tradition is to call that capital A. In other words, to use the same letter for the vertex as for the angle formed by the 2 lines meeting at that vertex. Yes, it's a bit of a confusion perhaps. It's possible to get a little bit confused, but in fact it makes things quite pleasant, because then we have 3 spherical distances, little a, b, and c, and 3 angles, capital A, capital B, capital C. So everything is a little bit symmetrical. So we have one angle A there, capital A, one angle capital B there, one angle capital C. So the capitals are the angles between the lines, and the little letters are the spherical distances joining points or between points. And what is spherical trigonometry? It's the study of the relationships between these 6 angles. And they're all angles. And the very important convention for angles. We are going to be using angles measured in radians. You might be a bit disappointed by that. You might think, why don't we use those turn angles you introduced in our last lecture? Well, first of all, this is classical spherical trigonometry, so it's classical that radians are used. But there's a good reason for it, because we're going to shortly see that the spherical trigonometric laws all involve the circular functions. And the circular functions are set up to work best with radians. So we're not going to use 180 degrees. We're not going to use half for this angle. We're going to use pi. Okay? All the way around the circle is 2 pi. 90 degrees is pi over 2, and so on. That's the system we're going to use. So our job is to now identify what are the main relations that hold between these 6 angles. And there are a remarkable number of relations. Not all independent. The relations are intimately interwoven, but there is a lot of them. So I'm going to now present to you the main ones, the most important ones. But before I do that, let me give you a very brief refresher on the main circular functions. Cosine, sine, and tan. Okay, there's a lot to be said about these, so let me just introduce them. Geometrically, the simplest way of thinking about them is no doubt in terms of the geometry of a circle. Here's a circle of radius 1 in the Cartesian plane, and a point on it making an angle x, let's say, with the positive x-axis. So this x is not necessarily related to that x. Maybe I should have used theta, but let's use x. What that means is that this length, the length of that circular arc, is x. That's the meaning of the angle x in radians. Now, associated to that point are these 2 projections onto the x and y axes. This point has coordinates cosine x. This point has coordinates sine x. Clearly, this coordinate is always between 1 and minus 1. And similarly, sine x is always between 1 and minus 1. And we think of this as being a functional relation. We think of x as being the independent variable. X is allowed to change. And sine x and cos x follow x. They are functions of x. So if you can imagine x starting here with 0 and moving sort of steadily in increasing direction coming all the way around, then this cosine value is going to be moving to the left. It's right 0 there when we're up at pi by 2. And then as we keep moving, it comes over here. And then to carry on, as the radius swings around again, it comes back and back to where we started. So as the point goes around the circle once, cosine x moves back and forth. But it doesn't do exactly this way linearly. It has an oscillatory aspect. Here's its graph. Now it's a function of x. And now I actually am labeling x here. X is 0. We have a value at 1. X is pi by 2. The value is 0. When x is pi, then the value is minus 1, and it oscillates back and forth. Similarly, when we start here, the sine starts at 0, and as we move up, the sine is going up, and then it's coming down, and then it's coming back up again. Okay, and it's periodic. And the sine graph is in blue here, going through 0 at 0, value 1 at pi by 2, value 0 at pi, and it has period 2 pi. There are other ways of thinking about the circular functions. In particular, there are what's called power series expansions for these functions. These are expansions that can be used to find approximate values for sine and cosine. These are the kinds of things the calculator uses. The series are actually infinite, but the calculator always just uses some finite truncation. So it turns out that the circular functions are much more complicated than people imagine. Their theory is rarely ever spelled out properly. Modern mathematics plays a clever game here. It's sort of like, guess where the definition is under the hat. In university level, the definitions of sine and cosine are relegated to the high school level. Oh, that's something that we learned back in high school. You already know what sine and cosine are. We don't actually have to give a proper definition. In high school, people wave their hands around and say, well, when you get to university, you'll eventually figure out what these things exactly are. So it's a very nice game, very convenient. As a result, modern mathematicians have a very ambivalent, sort of flexible attitudes towards the definitions of the circular functions. When it's convenient, the circular functions are defined in terms of a picture like this relating to the unit circle. In other situations, when the different need arises, they are defined in a power series expansion. Or they're sometimes defined in terms of connection with a complex exponential function. There's also infinite product formulas. And there are other ways, integrals as well, that different ways of defining the circular functions. Unfortunately, a consistent theory where one chooses one definition and then proves the other various things as theorems is rarely found. So I could go on about this at length. I better stop. In my Math Foundation series, I will talk at great length about this. But for now, let's just say that it's really quite problematic, and modern mathematics is very shady when it comes to these things. There's one other important function, the tan function, which is the ratio of sine x over cosine x. And that corresponds to the ratio of this to this, which is pretty well the slope of that line. So that's another geometrical interpretation. And it has a graph too, which is a little bit more complicated because it goes off to infinity periodically. So these are the main ingredients that we're going to need to describe the spherical trigonometry. And if you're not that familiar with these functions, or if you're not that happy with them, which I heartily approve of if you have that attitude, don't worry, I'm just going to state these theorems. We're not going to be using them at all in any kind of substantial way. Our derivation is going to be completely separate from this classical trigonometry. There's no logical link at all. We wipe the slate clean and we're going to start new and do it properly. All right. But I want you to see the classical formulas. And I especially want you to appreciate the complexity of the modern formulas, so that you will better appreciate the simplicity of the new formulas I'm going to show you in a few videos. So here's our spherical triangle. I'm now going to not bother putting the back of these great circles in. Just ends up cluttering the picture a little bit unnecessarily. You all realize by now this is a great circle. It actually does wrap around the sphere on the other side as well. So we have 3 points A, B, and C. We have spherical distances, little a, little b, little c. And we have angles, capital A, capital B, and capital C. And our first law is the spherical sine law. So all of these laws should probably have spherical in front of them because they're related to but different from the classical planar laws of planar trigonometry. The first one, the sine law. The sine of the angle capital A divided by the sine of the angle little a equals the ratio sine of capital B to sine of little b equals the ratio of sine of capital C to sine of little c. So the sine of this divided by the sine of that equals the sine of this divided by the sine of that equals the sine of this divided by the sine of that. The first cosine law. that the cosine of this angle equals cosine of little b times cosine of little c plus sine of little b times sine of little c times cosine of capital A. And if we like, we can rewrite that by solving for cosine of capital A. So this is just a rewrite. Cosine of capital A equals cos little a minus cos little b cos little c divided by sine little b sine little c. That's the first cosine law, because there are two cosine laws. One that has only one angle in it and three spherical distances, and this other one which has three angles in it and only one spherical distance. It says that cosine of capital A equals minus cosine capital B times cosine capital C plus sine of capital B sine of capital C times cosine of the spherical distance A. It's almost the same as the first cosine law, except for this minus sign. And of course the fact that the capitals and the small letters have been interchanged. So there are two cosine laws in spherical geometry. There are also two Pythagoras' theorems having to do with a right spherical triangle. So the first one is that if this angle A is pi by 2, in other words, if that's 90 degrees in degrees, or a quarter of a turn in turn angle language, or in other words, if this line and this line are perpendicular, well, then there's some special relationship. Then things simplify a little bit in this triangle. Here's the relationship. Cosine A equals cosine B times cosine C. So there's the hypotenuse and the two sides adjacent to the right angle. Cosine of the hypotenuse equals the product of the cosines of the two sides. And then there's another version, sort of dually, that we get when we have a spherical distance of pi by 2. So when this distance is pi by 2, now what does that mean? Well, pi by 2 is a quarter of the way all the way around. So if this is a great circle, then these 2 points are going to be antipodal. So they are actually separated by an angle of pi. And so if you take the midway point between these 2 points, then this will be an example of 2 points which are of spherical distance pi over 2 apart. So for example here, say on this blue equator, this one here and this one here, they are antipodal. And if we take some point about halfway in between, roughly about that one there, then that spherical distance between these 2 points, that would be pi over 2. So we're measuring in terms of angles, and we're looking at the angle subtended from the center by these 2 points. So in that case, there's then a relationship between the 3 angles. Sort of the hypotenuse angle at A, its cosine is minus the product of the cosine of B times the cosine of C. Just a little bit of a variation with the minus sign. Then there's 2 Thales theorems. One, again, with this situation. If A is equal to pi by 2, like this one here, then sine of little b equals sine of capital B times sine of little a. This name is my name for it. It's what I like to think of it as. It's probably not standard in the literature at all. And then the other Thales theorem having to do with this situation, same story. Now sine of capital B is sine of little b, sine of capital A. It's a good, interesting exercise if you have some familiarity with the power series expansions for cosine, if you look at the first few terms of this, so recall that the power series starts with 1 minus a squared over 2 factorial. Then there's further terms. Well, if you substitute the first two terms of those power series for both of those and expand out, then you get the planar version, a squared equals b squared plus c squared. And so the planar Pythagoras' theorem is a limiting case of this one. And in general, that's what happens. The planar trigonometric laws are limiting cases of these spherical laws. So the spherical laws are in some sense more powerful than the planar ones. Here's another rather useful law called the law of Haber-Sines. It's some kind of alternate form or variant of the cosine law, which is often in practice more useful than the cosine law, as it turns out. It involves a rather unfamiliar circular function called the Haber-Sine function. And it's defined in terms of, say, sine is sine squared of x over 2. Or using a trigonometric identity, one can also rewrite that as 1 minus cos x over 2. So given that's the definition of the Haber-Sine, here is the Haber-Sine law, again relating to a spherical triangle. And now I'm not even bothering writing down the sphere. Okay, you can see from the curved sides that we're talking about a spherical triangle, I hope. It's the same one as always. And the law of Haber-Sine says that the Haber-Sine of little c equals the Haber-Sine of little a minus little b plus sine a sine b Haber-Sine of capital C. So let's have a look at this. What is this actually saying? Haber-Sine of C, well, that's 1 minus cos C over 2. Haber-Sine of A minus B, that's 1 minus cos A minus B over 2. Sine A, sine B are familiar. Haber-Sine of capital C means 1 minus cos capital C over 2. So I'm just rewriting the law of Haber-Sines in terms of the more familiar circular functions. Now this is equivalent to, well, we can rearrange it a little bit. First of all, we can divide out by the common factor of 2, so that disappears. And then there's a 1 on both sides, which we might as well cancel. And then let's multiply everything by minus 1. So we get just cosine C on the left-hand side, cosine of A minus B over here, and then minus sine A sine B times 1 minus cosine C. Okay, what is cosine of A minus B? Well, it's a classical trigonometric formula that cosine A minus B is cosine A times cosine B plus sine A times sine B. So that plus sine A sine B will cancel with that minus sine A sine B, and they'll be gone. And we'll just be left with plus sine A sine B cosine capital C. And this we recognize as the cosine law. So this is just a rewriting of the cosine law. You can see they're pretty well equivalent. Just a few steps to go from one to the other. What's the advantage in this one? Well, roughly it is that the cosine function, when you have a value of c which is close to 0, the cosine function is flat. It's close to being 1. So that means you can move the value of x around and cosine of x doesn't change. It stays pretty well at 1. And so for small values of x, or for small angles, having a cosine in a formula is not really what you want, because you're getting something close to 1 and there's a lot of indeterminacy. So the advantage with this thing here is that you're replacing the cosine with, well, essentially a sine of x over 2. So when x is small, this is also small, and so it's more sensitive to small quantities. So in actual practice, it's quite a common formula for calculations. There's quite a lot of formulas that have half angles involved in them. So where we have not just expressions in sine and cosine of the angles A and so on, but sines and cosines of A over 2. For example, sine of A over 2, capital A over 2, is the square root of sine of S minus B times sine of S minus C divided by sine of B times sine of C, where S is A plus B plus C over 2. It reminds you of a Heron type formula or a Brahmagupta type formula. And then a corresponding one for the small a, sine of little a over 2. Again, a square root minus cosine of capital S, cosine of capital S minus capital A over sine B, sine C. Where S is now the sum of the capitals A, B, and C divided by 2. You can see here again some kind of similarity between the capitals and the little letters, but there is still some reasonable difference between the two forms. The duality between the little letters and the big letters is a partial duality only. There are, of course, many other formulas. Books on spherical astronomy are often full of lovely formulas. Some of them are a bit complicated. They're often not so easy to work with, and we can admire ancient astronomers and mathematicians who worked with these formulas essentially just with tables. They had to often compute the tables themselves before they could actually make the calculations. And in saying that, we should also mention that in order to work effectively with these formulas, we also need to understand the inverse functions to the circular functions. We've got to be able to recover angles from knowing the cosines or the sines of those angles. So there is yet more work to be done if you really want to establish this computationally. You need the inverse functions as well. All right, so here are Napier's analogies, not to be confused with Napier's rules. Tan of capital A plus capital B over 2 equals cosine little a minus b over 2 divided by cosine little a plus little b over 2 times cotangent of capital C over 2. Cotangent is 1 over tangent. And then there's a corresponding formula. Looks almost the same for little a plus b over 2, the tan of that. And here a different kind of formula, Delambre's analogies, where we have sine of an average over cosine of an angle equals cosine of a difference over 2 divided by cosine of a spherical distance. And there's variants of these as you rotate the letters around. There are quite a lot more spherical laws, and we might meet a few of them later on as we go. If this all sounds like Greek to you, these formulas are too intimidating, don't worry. Right? We're not going to be using them in any substantial way. This is classical spherical trigonometry. It's what NASA uses to send rockets to the moon. It's what satellites use to orient themselves. It's what global GPS uses. It's what navigation in the high seas is all about. How airlines figure out, how to go from one place to another. It's very important. These rules are actually used and practiced in many different contexts, in industrial contexts too. Anything involving spherical symmetry, probably these rules are not too far from the picture. So it's quite exciting that I'm proposing that we're going to replace all these rules. All right, we're going to just do it again. We're going to sweep the table clean and start again and develop much simpler, more powerful, more general rules that allow us effectively to make the same calculations, often more efficiently and more powerfully, without even, in fact, having to rely on calculators or computers. In principle, we can work by hand. So that'll be just a few videos away. We're going to have to set up a little bit more machinery. Next time I want to talk about perpendicularity on a sphere and talk about polarity and duality. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.